Sounds good.
Yeah. So yeah. So Alberto, you could start recording now, really. Okay. So good afternoon, everyone. Welcome to our icons seminar themed for learning for control and control for learning. And so icon is a center which was launched a year and a half ago. With the aim of addressing fundamental research challenges in autonomous and connected systems. So the center is co-directed by Professor Shreyas Sundram and myself, and currently has about 63 faculty members from more than 11 departments. And each semester for last year, we are organizing a bunch of seminars with a theme, like human-robot teaming, organized by Nira Jain, and this semester is learning for control, organized by Alberto and Masha. So today we have also a very nice researcher, Alex, and it's excellent research in this learning, uniform learning, and also control, especially on consensus. But I will let our seminar organizer, Masha, to introduce Alex.
So it's our pleasure to have Professor Alex Olshevsky here today. Professor Olshevsky received a BS degree in applied mathematics and BS degree in electrical engineering from Georgia Tech, and master's and PhD in electrical engineering and computer science from MIT. He was a postdoctoral scholar at Princeton and an assistant professor at UIUC. He's currently an associate professor with the UC Department of Boston University. Dr. Olshevsky is a recipient of multiple awards, including NSF Career Award, Air Force Young Investigator Award, Informs Computing Society Prize for the best paper on the interface of operations research and computer science, a SIAM Award for annual paper from the SIAM Journal on control and optimization, and an IMIA Award for best paper on clinical medical informatics. So without further ado, I let Alex start his talk.
All right, thank you very much for the kind introduction and as well for the invitation. It's my great pleasure to be here. My only regret is that it wasn't possible on my end to be there in person, but I guess this is life under COVID. So I'm gonna talk a little bit about some recent work trying to draw connections between reinforcement learning and gradient descent. And this talk doesn't assume you have any knowledge of reinforcement learning. The assumption here is zero, and I will introduce that kind of from the ground up. So this should be understandable at a level of, let's say, a first-year graduate student who's familiar with Markov chain. But I want this to be kind of interactive, so don't be shy if I say something and it's unclear or it's wrong and you want to tell me that. Just unmute yourself, interrupt, say something. If you type it in chat, I may not see it until the end of the presentation. Okay, so reinforcement learning, is an approach that's useful in many cases when exact models are not available. I'm not going to assume any background, and I think the first half of my presentation is basically like an overview of RL basics. All right, so the starting point is Markov decision process. So Markov decision process for me in this presentation is going to have finite number of states, not infinite, finite number of actions you can take in every state, and a Markov transition rule. So if you take, by the way, can everybody see my cursor? Yeah. If you take action A in state S, then you transition to a new state S prime, and the new state S prime is random. It's a function of your action A and your state S. It has the Markov property, which is that whatever you were in the past is irrelevant, and the probability is denoted, P of S prime given SA. And when you do this, you further get a reward, okay? So the reward you get is also random, but its expectation is denoted by lowercase r. And again, that also depends on where you are, what action A you take, and what new state S prime you transition to. And what you want is to come up with a good policy. A policy is a rule for choosing actions based on states. Policies can be deterministic or they can be random. So for example, what you can do is you can toss a coin. If it falls on heads, you choose one action. If it falls on tails, you do something else. And what you want to optimize the sum of all future rewards. Of course, when you take positive numbers and you add them to each other, you add infinitely many of them to each other, you might get plus infinity. So because of that, you introduce a discount factor gamma to normalize it. So if Ri is the reward, the random variable denoting the reward you get in the ith step of this algorithm, what you want to do is you want to optimize this kind of sum where you take R0 plus gamma R1 plus gamma squared R2 and so on up to infinity. Gamma is the discount between 0 and 1. And of course, you want to optimize this in expectation, where the actions are taken according to your policy, mu. So the policy, I guess I didn't say that the policy is denoted by mu. And this depends on your starting state as well, which is kind of here as a subscript of the expectation. So this is called the value function corresponding to your policy. And you want to find the policy with the best possible value function. It is not hard to see that, in fact, a single policy can achieve the best possible value function for all s simultaneously. Okay, but this talk is about something a little bit simpler, and it's the problem of just evaluating the value function. So the question is, I give you a policy mu, you give me the value function corresponding to that policy. It's a vector, I guess, with as many entries as the number of states. So why is this interesting? It's interesting for a number of reasons that I'll discuss, but one of which is that if you know the value function, you can use that to improve your policy, and this method is called policy iteration, right? And you know, we could say this in a lot of detail, but it's a little bit orthogonal to this presentation, so I'm just going to sort of, you know, sketch it out. You know, imagine you're trying to code like a self-driving car. I use this example a lot because I developed an undergraduate reinforcement learning class where at the culmination of it, you know, the students have to code a self-driving car in one of these Mario Kart games that completes the tracks. So imagine you have a red light, you have a choice. Do I speed up? Do I stay at the same velocity? Do I slow down? Well, if you could know somehow that the value function at the state where that you go to after slowing down is better than the value function at the state where you speed up or keep the same velocity, you can clearly use that to decide which action to take. All right. So the point is, knowledge of the value function can be used in what's called a policy improvement step, and you can just iterate that, and that procedure is called policy evaluation. So you want to evaluate the value function, but why is this difficult? It's difficult for two reasons. The first reason is that in some sense, you don't really know the MDP, right? I mean, let's imagine, for example, doing this again in the self-driving car scenario. Can you really write down an MDP that captures what is going to happen? Not really. You have to know something, but it's problematic to say you know the MDP and write it down. More common is the assumption that you can interact with the MDP. You can start it at a certain state, you can take a certain action, and then you can observe the next state. And you can then repeat it, take more actions, see where you end up, observe what the rewards are, and you can also reset it to the starting position. So that kind of assumption that you have access to a simulator of the MDP is more common, but it also means you don't a priori know all the transition probabilities. You can certainly learn something about them from repeated observations, but you don't know them a priori. Problem two, and this is even more important, is that there are too many states in any kind of practical situation. So again, think about your self-driving car scenario. How many possible states could your system be in? Essentially infinite, right? Maybe not literally infinite, since the number of pixels in an image is finite. But yeah, there are too many states. You can never write down this vector just by itself. All right, so how do you solve these problems? This leads us to a particular class of reinforcement learning methods that I'll discuss called temporal difference learning with function approximation. So the idea for temporal difference learning comes from the Bellman equation. So the Bellman equation tells you that the value function at state S is the expectation of the reward you get plus the discount factor times the value function of the next state you end up in, right? And this is the expectation when you take the action according to whatever policy, and the next state is generated according to the MDP. So just to maybe beat a dead horse a little bit, so the policy here is fixed. We're computing the value function. So this is the expectation when you take the actions according to the policy. And of course, this is obvious, when you take this kind of sum of the rewards, that's the same as the first reward plus the discount factor times all the rewards for the next time step. So this is kind of corresponding here. It's the first reward plus the discount factor. And you think of that as the value function of your next state. And so this leads to a very natural stochastic approximation type algorithm to try to evaluate the value function. The idea, and for this slide, we're just focusing on the problem of not knowing the MDP. So for now, we assume we can write down a vector with as many entries as the number of states, right? So you write down a vector with as many entries as the number of states. You initialize it, however, doesn't really matter. Then you generate a trajectory, state S0, then you take action A0, get reward R0, transition to state S1, take action A1, get reward R1. You generate the trajectory by taking actions according to the policy. And then you repeatedly update, you set your new estimate of the value function of state ST to be, by adding to it, some small step size alpha t times the reward you get on that transition, plus the discount factor times the value function, your current estimate of the value function evaluated at the next state, minus the current estimate of the value function evaluated at your current state. So why does this make sense? Let's kind of look at it and parse it. The idea is that you think of this thing that I'm circling with my mouse, reward plus discount factor times your current value function evaluated at the next state. You think of that as new information about the value of your current state, okay? So it's the reward you get plus discount factor times your current estimate of wherever you ended up. So that's like new information about what your current state is worth. And if that information is bigger than what you currently think your state is worth, you nudge it up. And if this new information is less than what you think your state is currently worth, then you nudge that down. And so at every step of this, this is called SARSA, because C-S-A-R-S-A. So at every step of this kind of method, you encounter one state, you update it according to this rule, and all other states are basically left unchanged. And that's how you update your vector. That's how you update your vector VT to the vector VT plus 1. So the key thing here is that you don't need to know the MDP. You just need to be able to interact with it. And this was invented in, actually, I'm not 100% sure, 1980s, maybe 1988 or 1982. Can't quite remember. So this kind of is a solution to the question of what happens if you don't know the MDP. But what do you do about the fact that your dimensionality of the states is huge? Okay, so there's a very natural thing you could do, which is that you don't try to update the vector VT because that has some enormous number of entries that you can't even access. What you try to do is you try to update some kind of lower dimensional approximation. So that's the idea. We're going to take the rule we just derived, and we're going to, instead of maintaining this vector VT, we're going to have a lower dimensional approximation. And that lower dimensional approximation is going to be parameterized by some set of parameters data. Okay, so the simplest thing you can do is to take a linear approximation. So how does this work? So basically what we're assuming here is that you take your MDP, and from every state you extract by hand with a certain number of features that you pre-planned in advance. For example, if you have self-driving cars and you have a bunch of images of what's happening around you, from that, using some kind of algorithm, you extract, is there a car in front of you? Is there a car behind you? What is the velocity of the car in front of you? What is the velocity of the car behind you? How far ahead is the car in front of you, et cetera, et cetera, et cetera. You write down a whole bunch of features. And so the assumption here is that you have some method which, given a state, will extract these features from the state. And the features, you decide what they are ahead of time and you write them down. And then what you have to do is what you're going to try to do is you're going to combine these features linearly using some coefficients theta to form an estimate of your value function. And the features are known in the sense of an algorithm exists to extract them, but the weights theta are unknown, and the weights theta are what you have to learn in this process. So the way you want to think about it is a priori, you don't know. For example, if you have a self-driving car, it is important that your velocity be related in some way to the distance that the car in front of you and that car's velocity, right? So it's a bad idea to be going really fast if you have somebody in front of you who's going slower than you are. But a priori, you don't know that. In fact, you're just going to interact with the system. Somehow these hard-coded variables are going to have to be combined to approximate that. Okay, and so phi L of S is our notation for the Lth feature at state S. These phi L's can be combined, can be put together into a vector, which we're going to denote phi of S. So the way you want to think about it is that, V has dimensionality, I don't know, 100 to the 100 to the 100 to the 100, some enormous number. And K, the number of features, is maybe 500 things that you've written down. All right, so with linear function approximation, you're basically trying to approximate the value function at state S as an unknown theta transpose times the feature vector at state S, which you can extract. So how are you going to learn this theta? So this algorithm that I'm presenting to you is called temporal difference learning, TD0 with linear function approximation. So you're still going to look at the very same quantity. You're going to generate a path. You're at state ST, you take action AT, you get reward RT, and you transition to the next state ST plus 1. And you're going to update theta by adding to it some multiple of this quantity G, which is written out over here. And let's look at what G is. G is the reward you get on the transition, plus the discount factor times what you think the next state you ended up with is worth, minus what you think your current state is worth. So if this whole thing is positive, this whole thing in the big parentheses is positive, you want to nudge what you think your current state is worth up. And how can you do that? See, before, when we maintained a vector, one entry for every state, it was very obvious how you would nudge it up. But here, what we're maintaining is some lower dimensional vector theta. And so you can't just change the value function of one state. You can change the theta, and that's just going to change the value estimate at every single state. So how do you update theta by to nudge up what you think the value of state S is? Well, the obvious answer is add a multiple of phi of S to theta. So what you do is you multiply this by phi of S and you add it to theta. Of course, there's a small step size alpha t in front. So likewise, if your new information, the thing I'm circling with my mouse, is less than what you think your state is worth, then this whole thing in the big parentheses is negative, and you're going to add a negative multiple of your current feature vector to theta, and that's going to nudge what you think your current state is worth down. So this is this is a stochastic approximation method. And the first analysis of this was due to what are now classic and celebrated results of Tsitsiklis and Van Rooyen, 97. They prove this works under various assumptions, and I'm going to kind of sweep the technical part of this under the rug a little bit. You need the ergodicity of the MDP with policy mu. You need, obviously, some assumptions on decay of step sizes, as you always do. You also need basically something that says the features are not redundant, else the whole thing can go to infinity. So you need the feature vectors to be kind of linearly independent. But that's not all you need. You also need a sampling condition. Sampling condition tells you about how the sample path is generated. And I'm going to describe the sampling condition on the next slide. So, yeah. Okay, so if you generate, the algorithm assumes the generation of the sample path. Now, given a policy mu, the policy tells you how you should choose actions at every state. So given a policy mu, you can write down the probability transition matrix just between states, just kind of like forget about the actions, right? So the probability of transitioning from S to S prime is the probability of transitioning from S to S prime given that you choose action A times the probability you choose action A. So then you have this probability transition matrix just among states. And the sampling rule is that you have to sample all these states S have to be coming from the stationary distribution of this P, okay? So the idea is you either have to compute P and initialize S0 at P, then all the rest of them, at pi, and then all the rest of them remain at pi. Or you just generate a very, very long path and you ignore the first part of the path until you think it's close to stationarity. And this is needed. There are counterexamples that show that if you generate this from a slightly wrong distribution, the method that I described does not work. Okay. And the last thing I'm going to tell you before I conclude sort of a summary of reinforcement learning is that there is a way to improve the performance of this method that's called TD lambda. What I have told you before is TD0, but you can do TD lambda. And the idea of TD lambda is you have an almost the same method, right? You perturb, you nudge yourself in the direction GT. This quantity in that I'm circling with my mouse in parentheses is the same as in the previous slide. It's called the temporal difference, reward plus gamma times estimate of next state minus estimate of current state. It's called temporal difference. But you multiply it not by the feature vector of your current state, but you multiply it by a decaying linear combination of all the past feature vectors you have seen since the beginning of your algorithm, right? So this is in the previous slide, this bit was just phi of st, but now it's phi of st times something plus phi of st minus 1 times something smaller plus phi of st minus 2 times something even smaller. And it's kind of maybe today, okay, I think people came up with this in the 1980s. Maybe today this is kind of very natural because, maybe it's reminiscent of Adam. You give yourself a momentum by doing something like taking linear combinations, decaying linear combination of past updates. But the high level idea is, yeah, if you keep encountering very similar feature vectors, this gives you momentum, right? Towards you take bigger steps. And if you encounter feature vectors that oscillate wildly, this kind of lowers the size of your steps. So this method is called TD lambda. Tsitsiklus and Van Roy also prove this works. The slightly stronger technical conditions, it's a little bit more convenient when you analyze this to assume that the algorithm went on from like time minus infinity. If you don't assume that, you have to introduce some error terms, which are also fine. But yeah, Tsitsiklus and Van Roy in 97 also analyze this. And they show that under the same condition this works. And you can think of this as stochastic approximation. Okay, so so everything I have said now is well known. Like I say, it's been understood since the late 90s. And this kind of concludes my overview of reinforcement learning. And by the way, if something so far is unclear, this is a good time to just pipe in here and ask me some questions. Now I'm going to tell you about some of my recent work trying to think these issues through. So what motivates me primarily, and I'm going to talk about some actual new kind of bounds and analyses, but the thing that motivates me primarily is trying to understand why these methods work, because they're a little bit weird, especially TD lambda is kind of weird. I want to have sort of a very nice, clear-cut reason to try to explain this in terms of things that we all know, like in optimization. And maybe to kind of understand the difficulty of analyzing this and how this differs from the kind of methods that you think about, is observe that what happens in these methods is that you use your estimate of the value function to update itself, right? And let me maybe go back a couple of slides to just a statement of TD0, right? Okay. There's a little bit of a delay when I press a button down. For some reason, this is slow. So it's like doing a control system with delay here, and I kind of failed at that. But okay, let's look at this equation. Right. So how you're going to update your value function depends on what you think what your estimate is of the next state that you encounter. So it could be a situation where your beliefs are basically correct and you progressively refine them towards optimality. Or it could be, perhaps, where you start with beliefs that are incorrect. And because you use your incorrect beliefs to update your beliefs just progressively get more and more incorrect with time, right? Because you can think of this inner product as representing a sort of belief on the value of your next state, and you can think of this inner product as representing a belief on the value of the current state. So why does it happen? Why do this kind of procedure leads to you getting things more and more correct as opposed to getting more and more wrong. I'm actually tempted, and I'll stop myself from going too far in this direction, but I'm tempted to make some kind of analogy to politics here. You know, there's all kinds of results in economics that say that rational agents will eventually agree given more and more information. But those kinds of results always assume we get some kind of unbiased samples of the truth. What if you use your current beliefs to interpret the information that comes in? You could just, you know, diverge off to infinity, an infinity of incorrectness. Let's put it that way. Okay, a related mathematical question is, what kind of convergence guarantees can you get for these methods? In particular, the issue that I'll come back to is what happens when the discount factor is very, very close to 1. Because if you think about the discount factor, in some sense, its introduction is a little bit artificial. It's there to make the infinite sum finite, but you want that discount factor to be very, very close to 1 because you want to capture something very long-term about the process. And in particular, you want to ask how it scales with the discount factor. Okay, so to address these questions, our starting point is this. You know what would be really, really nice is if these updates were gradient descent. Okay, they're never going to be exactly gradient descent because the updates are random, right? But maybe they could be gradient, maybe they could be SGT, maybe they could be gradient descent in expectation. So it would be nice if you could have an equation that says that the expectation of theta t plus 1 conditioned on theta t was theta t minus some small step size of the gradient of the function. So if you could write down a function like that, then that's it. You'd in some sense be done, right? Because you could use any of millions of analysis of gradient descent to analyze this. Unfortunately, this is not possible. And indeed, this observation is present in basically most textbooks on the subject. It's certainly in Sutton and Bartow's text, for example. You can see very easily, you can write down a couple of examples. The thing about gradient descent is that you can argue is a quality of mixed partial derivatives, right? If you differentiate something with respect to like x1 and then with respect to x2, it's the same as if you differentiate with x2 to x1. So if you write down these updates, the corresponding matrices, if you work out these updates with some simple examples, you should see that they involve multiplications by non-symmetric matrices, whereas gradient descent would result in symmetric kind of updates. So anyway, you can, let's just say you can rule out the possibility that these are gradient descent. And this has been sort of the starting point of all of the literature before the work that I'm going to tell you about. And the idea was, okay, well, it's not gradient descent, so we have to use, you know, various forms of stochastic approximation. For example, if you read like Borkar's textbook on the subject, that's very much kind of the approach taken. Okay, and I want to push back on this a little bit. And here's the core definition of this talk. I'm going to define something called a gradient splitting. This is a concept we're introducing. I've never seen this before. So let's say you have a quadratic, which I'm going to call lowercase f. So lowercase f is a quadratic. I guess lowercase a is the minimum of that quadratic, and capital A is the Hessian, and capital A is a symmetric PSD matrix. Okay, and then I'm going to say that a linear function, h of theta is b theta minus a. I'm going to say this linear function is a gradient splitting of this quadratic if b plus b transpose equals 2a. Okay, let's think about what this means. So a is some symmetric matrix, so 2a is some symmetric matrix. Let's say the ijth of entry of a is like 7, so the corresponding entry of 2a is 14. So this says that you can split that 14 however you want among the ij and jith entry of b. It can be like 10 plus 4, 11 plus 3, 7 plus 7. However you like, you take a non-symmetric matrix, you take a symmetric matrix and you split it into a non-symmetric matrix in this way. And by the way, whenever I say gradient splitting, that presumes if I say h is a gradient splitting of f, that presumes h is linear and f is quadratic. This is defined only for quadratics, not for any kind of other. All right, so why is this an interesting concept? It's an interesting concept for the following reason. Suppose h is a gradient splitting of a quadratic. It's immediate. Proof of this is like one line, that the inner product between h and the direction to the optimal solution, so the inner product between h of theta and a minus theta, is the same as the direction between the true gradient and the direction to the optimal solution. Well, up to a factor of 1/2, which I'm I'm gonna ignore here. So the point is, a gradient splitting still kind of points in the direction of the optimal solution. Here is maybe a graph, you know, you have A minus theta, you have negative gradient, they have a certain inner product. And when you look at the negative of a gradient splitting, the inner product is the same. Okay, here I drew it to have the same angle. Of course, it could be like twice as large in magnitude, and you know, the angle could be larger. It's the inner product that is preserved.
Alex, this is
Yes.
Shaoxue. Just a quick question
Yes.
about this gradient splitting. More like a previous slide. So is there any reason why you require this kind of equality here? Is it possible to say that, you know, this h perhaps, you know, lies in angle with the gradient like 90 degrees or, you know, less than 180 degrees? More like roughly the h could push the algorithm along the direction of gradient.
Yeah, okay. So I could relax it in that way. But for the application to reinforcement learning that I'm about to tell you, things actually work out very much nicely with equalities. So maybe let me hold off on this question and I will come back to it maybe 5 or 6 slides down the line.
Oh, thank you. Thank you.
By the way, are there any other questions? Feel absolutely free to interrupt or interject. Okay. So now let me make an observation that to those of us who kind of do some optimization is fairly trivial, which is that the analysis of gradient splitting is fairly immediate. Like, let's take a standard analysis of gradient descent where you set xt plus 1 to be the projection on some convex set omega of xt minus alpha t times the gradient. Okay, there's a certain analysis of it. I've posted this on the slide. I think everyone who works on optimization in the audience has done this, like at least, you know, a few times per semester we teach it. The key point is that, okay, I guess for those who have not seen this, anything like this before, you do a certain number of steps. You look, if you want to analyze gradient descent, you look at like square distance of the optimal solution, you expand. The key step is the inner product between the gradient and the direction to the optimal solution. You bound that in terms of some you know, f minus f star. And then there's some rearrangements and something like that. And the point I want to make is that this kind of analysis applies verbatim to a gradient splitting because, you know, the inner product's the same. So that's the only property here that's actually used, right? So if you want so for example, this particular analysis of gradient descent and a convex function applies to analyze gradient splitting of a convex function. Okay, so to recap, I have told you what temporal difference learning is. Then I told you it's not gradient descent, but then I told you that, you know what, if you have a gradient splitting, you can analyze this just like you would analyze gradient descent. And you can probably guess what the punchline of all this is going to be. Temporal difference learning is actually the gradient splitting of something, but of what? What is the function that the TD methods that I have just presented to you are trying to optimize? Okay, I need one slide of definitions here. So a couple of these are fairly standard when you're dealing with these with analysis of these methods. I'm pretty sure, for example, these definitions also appeared in Tsitsiklis' and McRoy's 90 paper. You look at the D norm of a vector. It's just the 2 norm, except you weigh each entry by the stationary distribution. Let's recall our setup here. We're trying to evaluate a policy. The policy is called mu. That policy induces a transition matrix between states. That transition matrix has stationary distribution pi. So you weigh things here by that stationary distribution. And also, maybe a little bit less intuitively, there's something called the Dirichlet seminorm. And the Dirichlet seminorm of a vector is the sum of the pairwise differences. It's the sum of x of s minus x of s prime squared, where you weigh this pairwise difference by pi of s times the probability of transitioning from s to s prime. And you sum this over all states s and s prime. So this is not a norm because when you evaluate this at the all-ones vector, it equals 0, right? If all the entries of x are the same, this is clearly 0. But apart from that, it satisfies all the other properties of a norm, so it is a semi-norm. And you can think of this as a measure of the projection of the vector x on the perpendicular of the all-ones vector, right? It's one particular measure of the norm on that subspace. And similarly, and I don't think I've seen this defined anywhere. This is I guess new with this work. I'm going to talk about the K-Dirichlet seminorm, which is exactly the same as the Dirichlet seminorm, except the matrix is replaced by its K power. Everything else is the same. Okay, so with this, I can tell you the first main result. The first main result, no, I pressed down main. The first main result is that temporal difference learning with function approximation is a gradient splitting of this function. And what's the function? It's 1 minus the discount factor times the difference between the value function and the optimal value function in the g norm squared, plus the discount factor times the difference between the value function and the optimal value function in the Dirichlet seminorm squared. Okay, I should say, what do I mean by optimal value function? Well, when we're talking about approximating the value function, we can't always assume that our approximation will be perfect. Remember how we're approximating things? We're extracting features from the state, and then we're trying to combine those features to make an approximation. So there is an optimal way in a certain norm that you can do this, and that is what those weights are denoted by theta star. Okay. So this, I would argue, gives you some intuition and some understanding of what temporal difference learning is actually doing. It's trying to do something more or less like gradient descent, except it's doing a gradient splitting, and it's doing this on this particular function. Likewise, we have the same kind of result for TD lambda. TD lambda is also a gradient splitting, but it's a gradient splitting of a different function that we write down here. It's basically the d norm squared plus the Dirichlet seminorm squared plus the 2 Dirichlet seminorm squared. That, remember, the matrix P is replaced by the, in the K Dirichlet seminorm, the matrix P is replaced by its K power, and going on so far to the 3 Dirichlet seminorm up to infinity with some kind of decaying weights, which are written out explicitly here. So all of these methods are actually very, very close to gradient descent, and they can be analyzed verbatim using tools from various gradient descent. Okay, I should say that this is a generalization of a really nice result by Jan Olivier that inspired this work, which showed that TD0 is actually exactly the gradient of the function f of theta when the Markov chain is reversible, right? And this result can be viewed as a generalization to the case of non-reversible Markov chain, in which case it's actually not the exact gradient. It's this gradient splitting. And the value of this is that in practice, of course, things are never reversible in the in reinforcement learning, because there's always good states and bad states, and policies try to bring you from good states to bad states, from bad states to good states. Okay.
Yeah, Alex, real stupid question. So
yeah, go ahead.
When you introduce gradient splitting, you'd introduce it for quadratic functions. Yeah. Are these quadratics? These functions, these Dirichlet norms and so forth?
Yeah. Because if you look at them, let's right. I mean, they're both okay. If you look at dependence on x, it's just different values of x squared, right? And these, once you fix the policies, these are fixed numbers. So these are both quadratics.
Okay. Got it. Thanks.
Mm-hmm. Yeah, and by the way, don't if you have questions, just jump in. Don't feel like you have to wait till the end. I'm sure somebody else has exactly the same question, so it's good to keep things clear. Okay, so this, I argue, gives you a new interpretation, but does it give you anything useful in terms of analysis? Okay, in order to do that, let's compare it to what people have done before and the kind of bounds this gives, the kind of bounds that people had before. I should say that once you've established this, an analysis of this is fairly straightforward. It's just an analysis of SGD, right? Actually, there's a little bit of a caveat, because when you do something like gradient descent with gradients corrupted by noise, typically you assume the noise is IID. Here, the noise is not IID because the noise depends on the state, and the state depends on the previous state, but the noise is Markov. So you actually need to analyze noisy gradient descent with like Markov noise. This is called Markov gradient descent. It's been analyzed in a number of papers. So this particular modification is also well studied in the previous literature and optimization. Okay, So let's make the following observation, that if you have a quadratic, then the inner product between the gradient and the direction to the optimal solution is proportional to the differences in the values, right? So just like when you differentiate, it's like 2a times theta minus a, and when you take an inner product with theta minus a, you just get 2f of theta minus f of a. And of course, f of a is 0. So this is a nice property of quadratics here that general convex functions lack. But the point is, all our functions are quadratic, so we just apply it to that. So this tells us exactly what the inner product is between the expected TD direction, which remember we called G. This is the expected direction taken by temporal difference learning, and the offset to the optimal solution. It's just basically it's this quadratic. And I think I may be missing a minus sign here. I think, yeah, because negative G is actually the direction it takes. Now, what did people use before us? Before us, the previous literature, you need, if you're going to analyze temporal difference learning, you need something like this. You need to kind of argue, on average, how much does your method make progress towards the optimal solution? Here, we're able to say exactly what it is. And Shashri, coming back to your question, this is why it's nice to have that equality there, because this allows us to say exactly how far temporal difference learning brings you on average to the optimal solution at every stage. Of course, you could replicate any theoretical results you have by like a greater than or equal, but it's nice to note they're exactly equal. Now, what people had in the previous literature was this inequality, which you can see is considerably weaker, or partially weaker, because it's essentially the same thing, except it's missing the second term. And the reason it's considerably weaker is that as the discount factor goes to 1, this always went to 0. So this was always a feature of the previous analysis of these methods, that if you set the discount factor close to 1, then it makes less and less progress towards the optimal solution. And what this meant is that there was a factor like 1/1 minus gamma in the various analyses that you give. But see here, you have this, but you also have a factor here that does not go to 0 when gamma goes to 0, when gamma goes to 1. And you can analyze it just based on this. Now, the little bit of a caveat is that this, as we said, is not a norm, it's a semi-norm. And that's going to complicate things a little bit. So here is what you can do. You can analyze, we actually analyze projected TD learning just to simplify things a little bit. And here is the kind of bound that we're able to derive. It's, again, fairly standard in the optimization literature. We take a step size of 1/√t, which is standard in this kind of literature because you don't want things to be scaling, at least here, with the condition number. Later, I'll discuss various things that do scale with condition number, but you want things that are independent of the condition number of the function that you're trying to do gradient descent on, and that can be accomplished with a 1/√t step size. Like 1/t step size would decay at a faster rate, but would also have that condition number in there. And the bound that you have is fairly kind of standard. You know, there's something depending on initial condition. There is something depending on the sizes of your gradients or the projected set. Because it's Markov gradient descent rather than normal gradient descent, some kind of mixing time also comes in there, which is defined here. Now, how does this compare to previous work? Basically, in the yeah, someone's going to say something.
Yeah, sorry for the interruption. So can you go to the previous slide? Yeah, so here my doubt is just like a clarification question. Is the first term is this norm D, and the second term is this the other norm, which was also depending upon K, and how that dependence of K is affecting its rate, or is it not important?
I'm sorry, what is K?
There was a K, like, which was the power of transition matrix in the definition.
Oh no, that was for TD lambda. That was for TD lambda. And by the way, there was a sum over K. So it was a sum over K. So actually, there was no K kind of in the final expression. It was like the Dirichlet norm plus the Dirichlet 2 norm plus the Dirichlet 3 norm plus the Dirichlet 4 norm with decaying coefficients, and that's where the quote unquote K come in. But anyway, that was for TD lambda. And yeah, like I say here, you can talk about what the result is for TD lambda. This is TD0, so here it's just the D norm plus the Dirichlet norm with these weights.
Thank you, sir. Thank you so much.
Are there any other questions? Okay. So this is, for example, from a Colt 2018 paper, which analyzed this method. And they have some kind of bound, which is very similar, but has this not so nice property that it has a 1 minus gamma on the denominator. So if you let gamma goes to 1, it blows up. Now, we can derive that bound from our theorem, right? We have basically 2 terms here. And if we just forget about the Dirichlet term, we cross it out, we have exactly their result from 2018. But we can also do the opposite. We can just forget about the first term and just focus on the second one. And if we do that, we basically get a bound for convergence to the optimal solution that does not blow up as gamma goes to 1. Now, the only hitch here is that the Dirichlet semi-norm is a semi-norm. It's not a norm, right? So in some sense, when you bound this, what you're bounding is not really the distance between what your algorithm outputs and the optimal solution. What you're bounding is something like the projection of it on one perp. But here's kind of the punchline of this discussion. I want to argue, actually, that's all that matters. Traditionally, this literature considers something like looking at the norm between the correct answer and what your algorithm outputs. And I want to push back on that too. I want to say, in fact, you shouldn't care about that at all. You should only care about the projection of your answer on one perp. And let me explain why that is. Again, think back to your car scenario. You know, you got your Mario Kart or whatever, you have a little traffic light, you're approaching it, you got 3 choices, you know, let's say slow down, keep your velocity the same, or speed up. And maybe your value function is something like, you know, -1 billion, -1 million, 0, because presumably you have some large negative rewards associated with collisions, and running through a red light is bad. And that's why you think in expectation it's like -1 billion. And so you know to choose 0, right? Because 0 is better than -1 million and -1 billion. Now here's the observation. You can take those 3 numbers, add some constant to every number, and it's not going to change anything, right? The only thing you use, your estimates of the value function, is deciding which one is bigger, right? That's all you use it for. You decide which one of them is bigger, and then you choose that. That's how the policy improvement stuff works. So anytime you have an error on one perp, that actually does not affect at all what you use your estimate of the value function for. And our observation here is that, in fact, if you look at this, the projection of one perp actually does not blow up with gamma going to 1. Okay, you can play various tricks on this. Like you can actually get, if you try to use these insights to get like a bound that's more comparable with this, you can, what you can do is you can push the 1/1 minus gammas into higher decaying terms. There's all kinds of tricks. One of the difficulties is that if you actually want to estimate the mean of the value function, it's probably you can't get rid of 1/1 minus gamma. So that will blow up as gamma goes to 1. But if you want to analyze differences, then what we're observing is that you can do that without any blow up with gamma. All right, now let me tell you one more thing. This is, I'm going to skip this. This is some recent results that I've just posted on the archive, I think like a week and a half ago, maybe. And I'm going to kind of tell it to you in 2 slides. I'm going to tell you another application of this gradient splitting interpretation. So there is something called a policy gradient method. And a policy gradient method has this, is the idea that what if you parameterize your policy directly by theta? Forget about the value function. You're just going to parameterize your policy directly. So for example, maybe you have 2 options at every state, and theta is a number between 0 and 1. And with probability theta, you choose the first option, probability 1 minus theta, you choose the second option. Okay, that's the toy example. More realistically is that your states are somehow vectors, and thetas are the weights of some kind of neural network. And you feed in your state to your neural network, and then you have an output. So any theta tells you rules to choose actions based on states. Think of each theta as defining not just one function, but as many functions as the number of states. Okay, well, you can do this, but what should you do with the theta? Okay, what you want to do is you want to do gradient descent on the value function. But that sounds like a tall order, right? Like I said, just estimating the value function is difficult. And if you want to do this, you need to be somehow estimating the derivatives of the value function to update your theta, right? Turns out this is sort of doable. This equation that I have in the bottom is called the policy gradient theorem. It was invented in 2000. And I'm going to be a little bit informal. I'm going to sweep some details under the rug. I'm going to say you can generate the state and action from a certain distribution. I'm going to skip what it is. It's a certain occupation measure. You can generate ST and AT in some way, such that if you update theta by taking a small step size in the direction of the value function of whatever state action pair you randomly generate, times the derivative of some log of this distribution of the action in the action you took in the state that the action you generated in the state that you generated, you plug in the specific values for that. You look at pi theta, you take the log of that, you differentiate this. If you do this, then that actually has expectation, which is exactly the gradient. Okay, but this obviously involves knowing the value function, which, as we just said, we don't know. So now you see another application of knowing the value function. If you know the value function, you can use this formula to estimate with noise the gradient of the value function, right? Which is something very specific in this scenario. Generally knowing the function and knowing the gradient of the function is not the same. But here, being able to estimate the function allows you to estimate the gradient of the function. Okay, maybe I spoke too much because, of course, if you know the function, you could form estimates of the gradient. So, okay, maybe it's not that unique. But in any case, you can do this. And this leads to what's called an actor-critic method. An actor-critic method says you do policy gradient, like I just told you, but you don't know the value function. Okay, but you're going to use temporal difference learning, the method I just described in the beginning, to try to estimate the value function. So you have two updates. One is the first one that I'm circling with my mouse is exactly the same from the previous slide, except instead of the true function, instead of the true value function, you have some kind of linear approximation. Now you assume you can extract features not from a state, but from a state action pair. And this here, the second one, is just TD0, but it's TD0 applied to the MDP on state action pairs. So what I told you before was temporal difference learning, where you learn the value function of a state. Here you try to learn the value function under a policy of a state action pair, right? Which means what you think it means, right? It's the value, the infinite stream of rewards discounted if you take that action in that state and then follow the policy. So you have two lines. One line attempts to use your estimates of the value function to estimate a gradient. The second one attempts to update your estimates of the value function using temporal difference learning. And they're coupled, right? Obviously, omega is used in here, and theta is used in here as well. You don't see a theta in this equation, but you generate these states randomly, and you have to generate the next state from the current state, and that depends on the policy. So the theta determines the policy, so that comes into here. And also remember, the sampling distribution in the second line has to be the stationary distribution of the policy. So theta affects the randomness in how you generate these state action pairs in a number of ways. So these two distributions are coupled. So this is called actor-critic. It was analyzed for the first time, I think, in the early 2000s. And that was based on a trick that was repeated in almost all of the follow-up papers. And almost all of the follow-up papers use a simple idea. And I don't want to go too deep into the technicalities here, so let me just describe this very, very informally. The idea is very simple, that under appropriate assumptions, you analyze this using what people call two-time scales. Two-time scales is when you let beta t and alpha t decay to zero at different rates, so that beta t decays a lot faster than alpha t. And the reason that this can be made with two-time scales is very clear, right? If beta t moves so much slower than alpha t, then from the perspective of the second iteration, the policy is fixed, right? The policy is fixed. The policy is a function of theta, and theta moves at a rate that is asymptotically negligible because of this relation. So from the perspective of the second iteration, the policy is fixed. And if the policy is fixed, you just apply any analysis of temporal difference learning, the one I gave you, or any other one. And then you get the statement that this converges to the best possible approximation. So if you make the assumption that the best possible linear approximation is good. In fact, the original paper which analyzed this by Konda and Tsitsiklis assumed the best possible linear approximation is perfect, the error is 0. So if you make some kind of assumption like that, then you just the first one just becomes gradient descent. All right. So using this trick where beta t over alpha t, using this 2-time scale trick, you basically get to decouple these two equations, and then you get to analyze them. But the problem with that is that this essentially artificially slows down one of the iterations. And what we have shown, this is joint work with Barman and Gressifard. This paper is the very last paper I have in the archive, is that you can actually choose these two things to be on the very same time scale. We choose 1 over square root of t, and you get a certain convergence time bound for this in terms of epsilon and the condition number of the underlying function. I should say convergence here is always to a stationary point, and convergence is here in terms of the gradients of the value function, because this iteration, the one I'm circling with my mouse, is gradient descent on a non-convex function, right? The value function there is not guaranteed to be a convex function of theta. So because it's non-convex, you always do convergence to a stationary point in this context. Anyway, so it scales, okay, as epsilon minus 2, mu to the minus 2. Actually, this is only the second paper to analyze this in the context of single time scale. And the bound we get is the best known bound. I think the previously best bound was published very recently, and it scaled like epsilon minus 2, mu to the minus 4. And the punchline here, and this is the very last thing I will say before I conclude, I know I'm almost out of time, so I'm going to make just one tiny point, is that there is a very clear intuition for why this works. That should be very natural given what I have told you. So why do you want to why do you want to use 2 time scales? Because you want the first iteration to be slower than the second. By the way, the first iteration is called the actor iteration. The second iteration is called the critic iteration, which makes sense. Theta is like what the actor does, and then omega is your estimate of the value function. So it's like the actor does something, then there's a critic who tells the actor, okay, this is how I think you're doing, and then the actor uses the critic's feedback to do something else. So that's why these are called actor-critic methods. So you want the actor to be slower than the critic. That's why you take this stepsize separation. But in fact, as we have just described, the critic does gradient descent on a strongly convex function with noise, while the actor is doing gradient descent on a non-convex function with noise. So it should be clear that the critic is naturally faster than the actor, because gradient descent on a strongly convex function is just going to be faster than gradient descent on a non-convex function. So this is okay. This is not quite an analysis, but just based on these kinds of hand-wavy arguments, it should be, I think, clear why an analysis here can be made to work. And with that, I will conclude. Just to recap, my kind of high-level agenda is to try to take methods in reinforcement learning and try to interpret them in terms of things that I see as more natural and more understandable, like gradient descent. You know, we understand gradient descent. We want to try to use these kinds of methods to analyze methods in reinforcement learning. I've told you about a couple of examples, like getting better bounds on temporal difference learning and getting better bounds on actor-critic. And more importantly, the bounds that we get in some cases have qualitatively different features than previous bounds. Like, for example, do they blow up as you set the discount factor to 1? We have some ongoing work. So we submitted something to the last ICM, the current ICML, about how you can use this to parallelize something like TD learning. After all, as many people in the audience knows, there's tons of work on parallelizing gradient descent. So if you think of reinforcement learning as being very close to gradient descent, surely you should be able to parallelize reinforcement learning, right? So, and some of our ongoing work has to do with using this work to do something with neural rather than linear approximations. In general, it's very difficult to replace a linear approximation with something like a neural network. That difficulty is not simply a difficulty of analysis, in that there are tons of examples where if you take these methods that I've given you and instead of a linear approximation, you use a neural network, they will just diverge, right? And this is a major difficulty that people in practice face because sometimes their methods work and sometimes their methods don't work. But there are some scenarios that suggest that under appropriate initializations and having the neural networks be sufficiently wide, their degree of nonlinearity is bounded. And we're trying to kind of work on that to get some results that show convergence in the neural network case under some particular conditions. It's sort of related to these results, but much messier because there is just no getting around making like a billion fairly ugly assumptions to get a result in that space. All right, and I guess with that, I will end and conclude you for thank you for your attention. And if there are any questions, I have all the time to answer them.
Fantastic talk, Alex. Thank you so much.
Thank you.
So I think we have time for a couple of questions from the audience.
I could ask another question. So the fact that your gamma can go to 1 seems to indicate that the average reward case somehow is captured by your analysis, right? And the fact that when it's kind of independent of this constant that you add, when you look at the average reward Bellman equation, that constant ends up being the actual average reward, right? You've got the value function plus the optimal average reward is equal to the whatever you get on the right side of the Bellman equation. Is that there? I mean, essentially, that's what's being captured by these results.
Yeah, that's a great question. I thought about it a while ago, and I didn't figure out what the answer is after a few days of thinking about it. Let me say it's not 100% simple, right? Because let's imagine all the rewards are like 1 for simplicity, right? So the average reward is 1, right? But if you introduce a discount factor, the reward is 1 over 1 minus gamma, right? So somehow what's being captured here is not quite average reward, but average reward even amplified maybe by, Anyway, something
so
along the line.
Yeah, normally you would do a 1 minus gamma times your value function, then take the gamma goes to 1. So somehow that 1 minus gamma has to come in, but it seems like all the pieces of the puzzle are there. There's some tiny little piece that needs to be put in.
Right. Okay. So what you're saying is right. So you have to, so when you go from that, you multiply by 1 minus gamma, right? Then you take a limit. Yeah. So presumably you should be able to translate this into a result in average reward. I tried it for a couple of days and I couldn't do it. Possibly if I tried harder, I could have done it.
Cool. Thanks.
Thank you.
Very neat.
So I had a question. So in the last part of your talk, you talked about actor and critic methods. Yeah. And you mentioned that typically actors, are slower than critics because they apply gradients on a non-convex function, but critic does so on a starting convex function. So can we sort of use, or people have people used variance reduced methods to sort of speed up the actor uplift?
Yeah, that's a great point. Can you use variance reduction here? Okay. In fact, and I think maybe many of you in the audience know this better than I do. So let's go back to my TD slide, my very first one. And I'm gonna kind of answer this question with a question because I don't know the answer. So let me kind of say what I think the difficulty is. Okay. Let's go back to just the statement of TD. Yeah, I guess this PDF has too many equations. So for some reason it's slow, but yeah, let's look at this here. Okay, So let's say you interpret this as a gradient of some function. Actually, we haven't, I think that's probably true. We haven't quite shown this. What we've shown is that the average of these is the gradient of something, right? The average of these is the gradient of something. That doesn't necessarily mean this one is the gradient of something. But okay, let's go with it. Let's just assume, even though this may not be true, that this is the gradient of something. I mean, this looks like basically you're taking a function randomly and taking a gradient. Can you use variance reduction? For example, variance reduction will give you a geometric rate, right? Can you use that here? Okay, possibly. One difficulty that I see, and I don't know to what extent this is kind of a killer concern in this application and to what extent it isn't, but variance reduction methods, all of them scale with the number of states in some way. So for example, the variance reduction method I know the best is SVRG. So SVRG will periodically go through all the functions and compute every single gradient. Even if they don't do it, they need to store something that's proportional to the number of functions, right? So is this statement of mine correct, that every single variance reduction method has to do something that scales with the total number of functions? If that is accurate,
I think I mean, when it comes to SVRG and Saga, yeah, you're right.
Yeah. Okay, but you know, there's a million variance reduction methods, and I only know SVRG. So, but anyway, yeah, that will not be super attractive in this context because, as I say, the number of functions is proportional to the number of states. The number of states is like number of images. But you know, maybe you should. Maybe there are some ways around it. Not 100% sure. But yeah, if you know, if you have any insight of this, because I'm fairly ignorant of variance reduction beyond SVRG, then I would love to hear that.
Alex, I think there is a question from in the chat window.
Yeah. Okay. So the question is, how do you initialize the weights associated with the features, and how do you initialize that? Okay. So let's look at it right here, actually, because this is the right slide. So I presume you're asking about how you initialize the theta, right? So arbitrarily, right? It doesn't matter. You initialize them however you want. And if you go back to, like the theorem that I have shown, I'm going to keep pressing down until I get to the theorem. Anyway, the theorem will have a term where it's like theta 0 minus theta star, right? So that's how you're, right here. That too fast. Hey, all of these results have theta 0 minus theta star squared, right? Somewhere in them. So it really doesn't matter how you initialize it, but if you initialize it poorly, you will pay something in that term. Okay, I think someone's raising their hand.
Hi, thank you, Professor, for the nice talk. I just have one question which is related to the previous query of variance reduction methods. So if we go to the final slides where you mentioned that, okay, that there is an existing Nix paper which talks about challenge square by mu raised to power 4, that result. So from my understanding of this 2 time scale algorithm, the existing literature tries to convert this 2 time scale to single time scale by applying momentum type variance reduction techniques to one update and then get a similar behavior where they do not need this beta t by alpha t goes to 0. And that they obtain by introducing that variance reduction to the update. But I think in your analysis, it is obtained much. So I was not able to understand the intuition how that thing is obtained. I just wanted to why that condition of beta t by alpha t is not longer required.
Wait. So I didn't quite follow what you said. So what you're saying is you can try to analyze this by doing variance reduction, or I'm sorry, not variance reduction, but momentum. You said.
Yeah, momentum-based variance reduction technique.
Yeah. And
that is the standard way to convert 2 time scale algorithm into one single time scale being used recently. So the intuition I want to understand is that there there is standard way how this beta t by alpha t going to 0 is not required. But in this analysis, what is making us what is helping us to not require this condition anymore? and obtain the better results.
Mhm,
Because,
mhm.
because in some sense now the 2 time scale algorithm has been converted into single time scale, because alpha t and beta t can be of the same rate.
So can I ask you a question? So you say you can convert a two time scale algorithm into a 1 time scale algorithm, right?
Yes,
But
yes.
what does it mean to convert it? Like, is the algorithm you implement, is that still 2 time scale?
No, I think maybe my understanding is wrong, but by single time scale, I mean they can be of the same rate. Like
Mhm,
the ratio need not to be go to 0. So
mhm.
it can be just for alpha beta t by alpha t can be 1, and like in your case, right? This beta t alpha t be multiplied by 1.
Okay.
I guess you maybe you are meaning that you know, for the fast time scale is assume they are reaching the equilibrium and then substitute into the slower dynamics, right? If you are meaning that, that's more like separation, the principle of time. So
Yeah.
Oh, is that what you mean?
Yes.
if that's what you mean, I think
Oh,
this
okay,
separation time is principle.
Got it. Yeah. So I think that is indeed what the previous work did.
I know.
With the exception of this one, as far as I know, this paper and the one I'm telling you about are the only 2 papers that did not use 2 time scales for actor critic, to my knowledge. I believe every single other one, okay, either use 2 time scales, or I should maybe qualify this, and since this is being recorded and I should be precise in describing the previous work. Another way that other papers have tried to do this is you say, okay, you use the same time scale, but you do a lot of critic steps per actor step. And it should be clear that that has the same effect, right? If you do many critic steps per actor step, then you can still maintain that the critic is going to be kind of converging faster than the actor. So for example, you can do something like, okay, one particular paper did something like during step I of actor, you do I critic steps. So the number kind of goes to infinity, or you can kind of set it to some fixed number if you know in advance how many actor steps you do. So anyway, as far as I know, except these 2 papers, all previous analysis relied on this kind of artificial slowdown trick. Yeah, let me just say that there are better rates you can get in non-convex optimization by adding a little bit of momentum to non-convex optimization. I think these are fairly recent results. Like I think it's called SPIDER was the acronym. I'm not 100% sure whether you could do it here, just because you have because these 2 iterations affect each other, right? So it's not like okay, if you assume the critic was always correct, then you could just add momentum here and just apply an analysis of SGD with momentum. But because these things affect each other, it's not immediately obvious how adding like momentum to the actor will affect the overall analysis.
Okay. Yeah, that makes sense. Thank you so much. And I'm
Thank you.
sorry if my question was not that clear.
No, this was an excellent discussion, and I definitely learned something.
Okay, thank you very much, Alex.
Yeah. Thank you, everyone. Yeah. So unfortunately, to keep up with the schedule, I think we have to end the talk. And yeah, so I want to thank everyone, Alex, and also the audience for attending the talk. And I guess Alex will go into talk, and you're going to have some meetings with the other faculty members.
Yes.
In a different Zoom link.
All right. Thank you for your attention. My pleasure.
Thank you.
Thank you.
Thank you. Bye.
Hey, Alex, feel free to take your break. And